Okay, everyone. So today, as we discussed in the last lecture, I'm going to run a lecture now so that we can catch up. And I've got a couple of problems for you guys to sort of work through at the end, but there's not going to be any submission for this tutorial, so you'll have a couple of problems to work through, but they're not due. And then at the end, we should have enough time in the 2 hours for me to be available to talk to you about your workshop if you have any questions or would like to discuss that in any way. So we'll motor through this as quickly as we can. So in the last lecture, we talked about fatigue. I started to introduce the idea of what fatigue is from an actual sort of a physical standpoint. Now what we need to do is get into the actual analysis of fatigue. And what we're going to be talking about first is this, what's on the screen there, is the fully reversed case. So the case where we have some sort of amplitude. Now that amplitude should be, that's interesting. Just taking this offline. Amplitude should only be from the centre up. I think that might be an arrow that starts there and goes there, and starts there and goes there, if we give them the very, very much benefit of the doubt. But amplitude, everyone knows what the amplitude of a sine wave is, and the mean is at the zero. Alright, so fully reversed case. So one example of this might be your shafts going round and round and round and round. If there's any bending on them, that is fully reversed. Now, if there's constant torque on them, then that's a different story because you have constant torque and alternating bending, and we'll talk about that as we get towards the fluctuating end of the spectrum. So that's not what we're talking about here. We're just talking about purely reversed stress. Now, I did these up, so we're going to analyse this a little bit differently to the way we've done it in previous years, okay? So anyone that's seen previous lecture notes, or if you come across any of my previous exams or quiz solutions or anything like that, you'll see that we're doing this a little bit differently. Reason is, you'll get exactly the same number, but the way that we've done it in the past was based on another textbook that sort of was the traditional textbook for this subject, and it's a little bit confusing. So I've kind of rewritten it a bit and used a bit of that textbook and a bit of the current textbook that you're using and some other things. So if it all looks just a little bit different to what you've seen if you've done the subject before, or if you're looking at some of the previous subject notes, that's why. Now what you're looking at the screen is, that's our static analysis workflow. That's what you did in the quiz, right? And the first thing we're doing is evaluating the forces, and you see the little dotted line goes off there to the left, and we've got free body diagrams and shear force diagrams and so forth. Everyone's super comfortable with that. The next phase is the determining the applied stresses and candidate critical locations, and there's lots of things that we have to do at that step. We understand the types of stresses, so that's our sigma equals MC on I for bending and so forth. And we talked about getting through the actual working out where the maximum for each of those stresses was through the cross-section that we're interested in, or a couple of candidate cross-sections. We talked about applying stress concentration. So if you have bending, you calculate the stress concentration for the bending based on the appropriate graph, and for torsion and for axial and so forth. And then we had a stress element and we calculated vectors for it, right? And either it was really obvious where the critical stress element was, or perhaps we needed one or two of them. Alright, now the next one down here, we determine our comparison or comparative stress metrics, and that goes over here to the left. And that involves, a lot of the time we use more circles. We calculated our principal 3 stresses and our shear max. We can calculate our von Mises at that point, because that's a really good comparison. So if you've got 2 or 3 critical stress elements, calculate a von Mises, and the maximum von Mises should be your critical stress. And then we can confirm the critical stress zone if that's required. So if you've only got one, then it doesn't really matter, but that's all good. And then the last step there was to compare whatever metrics we had to our failure criterion. In the static case, we had maximum normal, maximum shear, and maximum distortion energy, and those are the equations for those there. Final step, is it safe? Cool. So this is just a flowchart version of everything we've been doing semester so far. The reason I did that is because now we're going to slightly modify the flowchart a little bit. Alright? Pretty much the same deal, but now we need to start thinking about fatigue rather than static loading. So the first thing, evaluate forces. It largely doesn't change, okay? So free body diagram, shear force diagram, bending moment diagram, so forth. But what we need to do is understand the cyclic nature of those forces. Alright? So remember that we're just talking about fully reversed bending, or fully reversed, stress. And what we need to do is understand what's that going between. So what is the maximum, what is the minimum? And in this case it's going to be positive F minus F, positive F minus F, because it's fully reversed. And because you have a relationship between stress and force that's effectively linear, then that's what's going to be happening to the stress as well. Now, in the fully reversed case, we just deal with the maximum. Okay, so if you have positive F and negative F, you don't need to analyse for negative F, we're just going to analyse for positive F. And then when we get to the end, we're going to be comparing to Sn that we get from those curves, right? So we've got, I didn't put them there, that's all right. So Sn is what we're getting from this RR more bending test, right? And Sn is the value, or Sn dashed, and then we modify it. Is everyone see my cursor there? Yeah. So Sn is the value at the top of the curve here. And the actual test result, so if we calculate the bending stress, we just say, alright, let's say the bottom's in tension, sigma equals MC on I. I can calculate the stress at the bottom, and then that piece of material will travel around to the top, and it will be negative, that value, which is exactly what we know about bending. It goes around to the bottom and it's positive again. Okay? But what we say, that SE dashed or Sn dashed value that we use, is just one of those values of stress. It's the positive one. And we know that it goes from positive to negative to positive to negative. Alright? So if we have our criterion, our maximum stress that goes from positive to negative to positive to negative, so this is Sn dash, and we analyse the positive, and we have some actual applied stress, let's say. And let's say it's von Mises, which I'll talk about in a second. Sigma dash max, say, but we don't put that on there. Now if I can compare that point to that point, that gives me the same ratio as comparing that point to that point, or this point to this point we don't really care about because it's not critical. But can you see that because the curves sync up, because by, we're making them sync up, right? We don't need to analyse some sine curve compared to some sine curve. We just need to take a maximum point on the two curves and compare that, because that represents the entire time series. Okay? So when we talk about this, we analyse, and so even in this very first evaluate the forces, we're analysing that maximum force. But that maximum force is representative of the whole time series of force, and then you convert that maximum force to our maximum stress and compare that to the maximum allowable, and that will give you your factor of safety, but it's representing the whole fatigue case. Okay? Because this is measured in fatigue. So when you measure your critical limit in fatigue and you compare your actual applied in fatigue, then it's apples with apples. Alright? So that gets a bit confusing to some people sometimes, so I figured I'd clarify that a little bit. When we actually have a curve that doesn't look like this, obviously we'll need to shift our criteria, what we actually measure in the experiment, up or down, and we have techniques to be able to do that. So when you look at the forces, in this particular circumstance, make sure the force is fully reversed. Force on, force off. If you just have a force going on and then going to zero and going on again, you can't apply this analysis technique. We have to do something more advanced, which is what I'll show you later. Alright? So when you're looking at the forces, make sure that they are in fact fully reversed. Next thing, determine the applied stresses. Exactly the same as before. Alright, so we know stress types are available: bending, shear, transverse shear, torsion and so forth. We can use exactly the same stress profiles, except we need to remember that it's cyclic. So remember, our bending is maximum in top and bottom, but if that shaft's spinning around, then that's actually spinning around on the shaft as well with it. So just keep in mind that. But when we're talking about bending, we're analysing a single point and then assuming that that single point is cycling like this, so then that's okay. But just at this point, I've just put there, just remember that it's cycling just in case something funny is going on. And then we apply stress concentration, and this is one change for this year. Last year we used to do this on the endurance limit modifying factor, alright? But that gets a bit confusing because you guys know that you can calculate a different stress concentration for each type of loading. So bending, axial, torsion. And when you only have one factor on the right of the equation, it gets a bit confusing which one of those you use. Whereas on the left, we can apply this to every single element of stress, every single vector of stress for the particular components appropriately, and it works out fine. Now, the one thing that we need to do differently with fatigue, in static loading, you can just use that KT value that you read straight off those tables, because in static loading, everything pretty much works the same with stress concentration. It's just a geometric factor. But with fatigue, different materials are more or less sensitive to stress concentration in fatigue. Okay, so we need a little bit of a change, a little bit of a different way. And this equation here is the one that we use. So Kf now, so K for fatigue, I guess, equals 1 plus KT that you read off the table, minus 1, all in brackets, times Q. And Q is the notched sensitivity. Everyone look at your handout, the endurance limit modifying factor handout with the 4 tables and so forth on it. Right, the bottom 2 graphs. The bottom 2 graphs are your notch sensitivity. Now, if you look at that and you actually read the headings rather than just use the table blindly, the bottom left one is notch sensitivity charts for steels and 2024T wrought aluminium alloys subject to reverse bending or reverse axial loads. So the bottom left one is bending and axial. Alright, so if you're calculating a stress concentration for bending, you take the stress concentration KT value for bending and then the Q value for bending, and you get a KF for bending, and you apply that to the bending vectors. And then on the bottom right you see notch sensitivity curves for material in reverse torsion. So if you have torsion on your elements, you calculate KT for torsion, you calculate Q for torsion, and then you get a KF for torsion, and you apply that to the torsion vector. Okay? Now, just to read it, look along the horizontal is notch radius. Goes from 0 to 4 millimeters in both cases. And that's millimeters, so if you have inches you'll have to convert it in this case. And look at what those lines do as you get to 4. If I had a notch radius of 10, what do you think the values would be? Pretty much whatever the values on the right hand edge are, yeah? They look like they effectively plateau out to constant. And then I look at my SUT, and so you've got the black lines of steel and the dashed lines aluminium on the left. And so if you have different ultimate tensile strengths, the higher the tensile strength, the closer to 1 that notch sensitivity is. And then so you read that off, and then off to the left you get a notch sensitivity that you throw into that equation. Cool? Easy enough, pretty straightforward. Over on the right there, a little bit more complicated. The bottom line's aluminium. The top one's quenched and drawn steels with Brunel hardness greater than 200, and the middle line is annealed steels with Brunel hardness less than 200. That's just the graph that we've been given. Brunel hardness, there's a table in your textbook and an equation that relates Brunel hardness to ultimate tensile strength. Has anyone found that? Have we used that yet? I think it's chapter 8, but if you look up your index for Brunel hardness, it will give you an exact page. And I think it's about somewhere around the 450 mark is that 200 cut off, I think. But we can confirm that. If someone's got a textbook, Billy, you want to look that up or something, we can confirm that. So again, it's just based on the ultimate tensile strength. It's just expressed in terms of Brunel hardness in that plot. Alright, and then once we have that, we have the stress element and vector. So it's exactly what you did before, it's just an extra little equation and an extra little value that you do on the stress concentration. Is everyone comfortable with that? It's not overly complicated, it's just that because we are in fatigue, we need to do something slightly more complicated with the stuff. Are we looking up Brunel hardness? That's the section, yeah. Is it a table somewhere? That's okay. I'll look it up at the end of this lecture and then we'll have a go. Alright, so that's determining your applied stresses. Part 3, I haven't said calculate Moore's circle and sig 1, sig 2, sig 3 or anything like that, because we always use von Mises. If it's steel, we use von Mises, right? So now that you know what the other things are, in some circumstances principal stresses are going to be very important and you can calculate them. For static loading it's important, for brittle loading it's important. For fatigue, calculate von Mises. There should be a big table. Nah, it's alright. I'll look it up later. Okay, and so you calculate your von Mises, and remember we're calculating von Mises at a single point. That's our maximum point, but this is representative of a curve that goes between positive that and negative that, positive that and negative that. Okay? And at that point you can work out if there's more than one critical zone, then you can work out which one's the worst. And at the end, the last step, as before, we compared a failure criterion. In this case, our failure criterion, I showed you on a slide at the end of the last lecture, is n equals Sn on von Mises, and that Sn is this equation. We take our RR Moore bending result for probably 10 to the 6 is what we use for steel, 10 to the 8 for aluminium, and we modify it with all of those different factors. Okay, so can everyone see that it's basically the same workflow, you just change a couple of the equations and do a little bit more work and then you're there. Okay? So when we get to that fluctuating stresses, we're going to have to do a little bit more work at this end point to work out where we're at. But for the moment we're pretty much doing exactly what we did before, except we're using the fatigue equations. Alright, so showed you this in the last lecture. We talked a little bit about this. So the last thing to do before I can give you guys a problem to actually work through is to explain what each of these factors actually mean. Alright, CA is size factor. I talked a little bit about that, right? So effectively, if something's bigger, there's more likelihood that you're going to have some sort of a fault or small bubble or microflaw that will initiate fatigue failure. So the bigger things are, the more susceptible for fatigue they are. Okay? And so we have our RR Moore bending test. It's a really nice, completely specified test, and the diameter is something in a 20 mils or maybe 8 mils by the looks of that. Yeah, that would make sense actually. So let's say that RR Moore, the standard says that needs to be 8 mil diameter on the test. Anything bigger than the 8 mils is likely to be more critical. Smaller than the 8 mils isn't a problem for us because it's less likely to fail than the test itself. And so you can see that CA equals 1 if we're less than or equal to the same size as the RR Moore test. And it equals to this equation if we're between 8 and 250 mils. No information for greater than 250 mils. You can actually calculate that yourself once I show you how. Now, this equation, people mix this one up quite a lot, alright? D must be in millimetres. Doesn't work if it's in inches. You could probably calculate a version of this for inches if you want. Negative 0.097. The number of times I see 0.97 or positive 0.097 or someone using meters rather than millimeters or whatever. This equation, pay attention to it, make sure you got the right signs and decimal points and all the rest of it. That will give you your CA for a rotating circular section. Remember our RR Moore test is a rotating circular section. So we're not doing any different loading to what the test is, we're just talking about size difference at the moment. I've got a slide in a minute that'll talk about something different. Now, if you calculate CA and it's 0.5, is that correct? Now this is our rational thought process here. Think about what CA, CB, CC, etc. do. should they be making SN dash more or less? Less? Everyone think about that for a second. More or less?
More.
More? Is there a different option? So, what do we need this to do? This is effectively our yield stress. If I increase the yield stress, is that good or bad? Good. Would we expect damage to increase the yield stress or decrease the yield stress? Decrease. Yeah. So, if you look at this number, and you get a modifying factor that increases our endurance limit, is that correct? No. You shouldn't be increasing an endurance limit unless you're like coating it in titanium or something, and we don't have factors for that. Alright? If you get something that's 0.5, alright, 0.5 is decreasing it, good. If you get something that's 4.8, increasing it, bad. You've screwed something up. Okay? So this is our rational thought checks and balances shit that we're talking about, right? So when you get one of these factors, it's not a black box, and out of all of the equations that you'll use, this one's the one that you're most likely to put a wrong number in and get something that isn't less than 1. So when you calculate it, if it's not a nice, correct, between 0 and 1 modifying factor, you stuff something up and you need to calculate it again or work out why it's wrong. Okay? So just keep that in mind. Alright, now, obviously we don't always have rotating circular sections. We need to be able to calculate these things for more than just those particular loading scenarios. So, this one here is non-rotating circular sections in bending. Let's think about for a second what that means. Circular section in bending but not rotating. Okay, so we've got critical stress at top and bottom, but it's not rotating, so what that means is bending goes on the other way, bending goes on the other way, but it's not rotating, so the bending isn't just in one direction, it has to change directions. But it's a circular section, and this equation, big D, is the actual diameter. Okay? And then you multiply that by 0.37 to get little d, and you throw little d into this equation here. Okay, so you're calculating an equivalent diameter for the non-rotating section. And you can see that the equivalent diameter of the non-rotating section is smaller than the actual diameter. It's about a third. Yeah? And the reason is, if it's not rotating, that critical stress is only occurring in one little zone or two little zones, one at the top, one at the bottom. Whereas if it was rotating, that zone would be spread all around the outside surface of that circular shaft. So if you've got less area where the critical stress is going to happen, there's less chance that there's going to be a microfloor in that region, and so there's less chance that it's going to fail by fatigue. Right? So you're about a third less chance of failing by fatigue in this particular circumstance, aside from the fact that technically this isn't a linear equation, but you know, you can calculate exactly what the fraction is.
So sorry Dave, just recapping, we get the little d value from this for a non-rotating member, and then we sub it into the CA.
The other equation, exactly, yeah. So let's say we have a 20 millimeter diameter shaft, not rotating but in fully reverse bending. It's 0.37 times 20 gets you a new diameter. That new diameter goes into that 1.1 whatever it is times d to the power of minus whatever it is. That bad boy there. So you throw that 0.37 times 20 in that. Cool? Alright, so that's our equivalent diameter, because what we're trying to do is get back to a point that it's like our rotating bending test, alright, because we need to relate it to that. Now the next part is a non-circular section in bending. And our non-circular section in bending is effectively, this is an equation for it for a rectangle. Once again, if you have the height of the rectangle and the breadth of the rectangle, you can calculate an equivalent diameter, just 0.808 times the square root there. and that equivalent diameter goes back into the equation we had a second ago. Okay, so once again, if you have that geometry, this is not rotating, this is like our rectangular beam with force goes down, force goes up, force goes down, force goes up. You can calculate your equivalent diameter, and then you can calculate your C, what are we talking about, CA, using this equation. Alright, now let's talk about Y. Alright, because it's all good and well that you guys can apply those things, but I've given you effectively 3 equations for 3 geometries, and you guys will be dealing with a lot more than 3 geometries in practice. So you need to actually understand what this is. Okay? And the idea is that what you're trying to do is find the area where the stress in that area is greater than 95%. So if your maximum stress is 100 megapascals, anywhere where the stress is 95 megapascals or more, that area is the area that we're interested in. That area is the area where we need to know the probability of there being a microfloor there or not. Okay? And so for the rectangular case that I was just talking about, this is our bending stress profile, right? And so if our maximum's out here at 1 or, whatever, then at 95, and because it's a linear line, you can just, measure this and go, 5% back this way. This amount here and the same amount down the bottom, that area is the area we're interested in. That's our critical area. That's the area we don't want a microfloor in. Okay? And so to get back to our equivalent diameter kind of thing, effectively we take that area and get an equivalent circular section and use that as our point of comparison. Okay? So you can actually calculate these things. You can prove that equation. So that equation for CA that I gave you, you can actually derive it yourself doing this. And if you get a more complicated section, we can do all of those types of things. Now, torsion is going to be very similar to bending and rotating bending. Remember that the rotating bending has that, what was to draw it? So if that's our circular cross-section, our bending looks like this, right? Technically into the page. So we have our maximum out here, but if it's rotating, it's that maximum that goes all the way around there. And if you think about torsion, it's exactly the same. Torsion, the profile's like that, except it goes the other way. And once again, it's that outside sort of 5% that is going to be critical. So the equation that works for bending from the rotating bending test is identical to the equation you would use for torsion. In axial loading, remember that the forces or the stress is even throughout the entire cross-section. So that's why for axial loading I've got CA equals 0.9 because of that experimental data that we talked about, that because the force is everywhere or the stress is everywhere, then you've potentially got a lot worse circumstance than this. So you've got all of this area here where a microfloor might actually cause you a problem. So that's why it's 0.9. Okay? So it's a little bit difficult to get your head around at first, but once you apply this a few times, it becomes very, very straightforward. All right? Most of the circumstances will deal with a very straightforward. It's only once you do things in later years that you'll come up with a geometry that seems strange to you or a loading scenario that seems strange, and you'll actually have to come back to these notes and have a bit of a think about how to formulate one of these things. Alright, surface factor. Surface factor is easy to understand. Rough surface bad, smooth surface good. Yeah? Rough surface, lots of peaks and troughs and valleys, and any number of those could be a big stress concentration on a microscopic level and cause a crack. Bad. Our experiment is done with a mirror polish. Good. So if you don't have a mirror polish, you need to have some sort of a factor that accounts for the extra badness that is your surface finish. And that's effectively what this does. So A fine surface finish is good, and so our endurance limit will increase. A rough surface finish is bad, and our endurance limit will decrease, meaning that our factor needs to be less than 1. Now, in your textbook, figure 8.13, and I've reproduced it on the handout, so it's in one handy place. Top left, that's your surface factor. Now, everyone get your sheet out, and on that surface factor, I've labelled it CC, which is what it was last year, but this year it's CB. Pay you to just and replace that with a B. Alright, pretty straightforward. Look at the very top line, which is technically the very top line of the grid, and you've got an arrow going to it, mirror polished, and for any tensile strength the factor is 1, which makes perfect sense to us because our experimental specimen is mirror polished. And so if we have the same surface finish as our test specimen, we shouldn't have any modification to the factor at all. Next line down is fine ground or commercially polished. So that's about as good a surface finish as you're going to get in a machine shop if you specify that they grind it after they do some sort of milling process. Alright, so just on the mill or the lathe or something like that isn't going to get you this line. This line is then they put it on a proper honing machine or something like that they actually get a really nice finish. It's not mirror finish, because mirror finish is going to cost you a lot of money. But it's very, very smooth. It's taken any of the burrs away. Alright, and you can see that along the horizontal axis we got tensile strength. The first one is in KSI if you have it in KSI. The one below it is in GPA if it's in SI units. But it's all the same. So 400 megapascals is our left-hand end, and 1.8 gigapascals is the right. And so you just choose your tensile strength, and then you move up to that line, and that line's 0.9 until you get very, very, very strong steel. Next one down, machine or cold drawn. Machine is the sort of finish that you get off a lathe or a mill or something like that, assuming your tradesman knows what you're doing and it's not you doing it in a garage having not done the trade, if that makes sense to you. Right, so this is someone that knows what they're doing, trying hard to make that surface look good, but not any further processes after the actual machining process itself. Or cold drawn. Anyone know what cold drawn is? It's kind of like extruded, that kind of thing. Like cold drawn is the material's cold, but you can actually roll it and move it like that. So any rolling, bending, stamping type process. The next one down is hot rolled, which is, I suppose the surface is a little bit less because it's a bit more malleable. And then as forged, so that's kind of cast or any forging processes or things like that that hasn't had a subsequent machining process done on it. And then you see a couple of dotted lines there. One's corroded in tap water and the bottom one's corroded in salt water. So obviously that corrosion's having a huge effect on how good the surface finish is and how that surface finish is going to actually fatigue. So you can imagine if you've got a beautifully machined finish, and let's say we have a 400 megapascal ultimate tensile strength, our beautiful machine finish of 0.8 for our factor over on the left there, and now we've just let that get rusty, we're down to 0.45. And if you don't have a factor of safety of 2 or more, you've just fatigue failed. Simple enough? So, rust makes a difference. And if you are assuming that the finish that you've put on it as you put it into service is the finish that's going to last on it, then you better make sure that that's in the maintenance requirements, because otherwise they're going to let it rust and it's going to run. Cool? Alright, everyone good with that? Easy enough. Temperature factor. We used to do a really simple one. This is a little bit more complicated. In the textbook, this is what they actually use for temperature factor, so I think it's pretty good. The one in the textbook, this equation is given to you in the textbook in terms of Fahrenheit, degrees Fahrenheit. I have reformulated it here in terms of degrees Celsius so that you have both. Very easy to formulate if you know the equation between degrees Celsius and degrees Fahrenheit. Effectively, if the temperature is below 450 degrees Celsius, temperature has no effect. Alright? If the temperature is between 450 and 550, then you use this CC equation, so you sub your temperature in there, and that will go anywhere between 1 and, what was it, 0.45 I think is the upper limit, so at 550 it's about 0.45. If you're not in that range, then you've stuffed up the equation, or I have, so double check. But if you're not in that range, then something's going wrong, and double check the way you've used the equation. And anything above 550, particularly if it's a mild steel, that's outside the realms of this analysis. All right, you are no longer able to use idealised RM or bending test results and convert them. If you are working in that range, you need to do the experiments yourself on the steel at that temperature for the experiment. All right, and get different results. So I've put 0 there because once you put 0, you've got effectively infinite, and well, you know, it kind of screws everything up. So actually, that should be infinity probably rather than 0. But anyway, what do we want our Durance limit to be? You want that smaller or bigger? No, smaller. Small's good. Yeah, so 0. That's right. All right. Anyway, you can't analyse it there, so don't. If you've got it hot, check it. And the reason is, I've put a couple of slides just here on the reason. Have you guys done materials? If you know the phase change diagrams for steels, right? So I've got one on the board there.
Yeah, we did.
Look at that line. The horizontal line there is at 727 degrees Celsius. So conceivably up to 727 degrees Celsius, your crystalline structure's changed entirely. But if we look over here on the left, and this is our mild steel, which is about 0.05% to about 0.25% carbon content, and you see you've got this diagonal line coming up there. If you're at the very low carbon content of mild steel, it's about 550 where that line starts to cross there. And so just to be safe, that 550 mark is about where we're confident, below which the crystalline structure is still what we need it to be, above which it's anyone's guess. If it's low carbon, you're stuffed. If it's high carbon, it might be okay, but it's not something that you can just put an empirical equation on and say, yeah, it'll be fine. You need to do more work. Right? And a little bit safer, so that's a medium carbon steel, so about 0.25 to 0.5, and that's high carbon steel, so 0.5 to 1. You got ultra high, which is up to about 2, I guess, after that, but I haven't talked about that. But that's really the rationale for why we have that temp factor there and why that's the limit on it. Because any hotter, even though you're not molten, even though it's not, you know, changing in that respect, it is changing the crystalline structure, which changes the way that force gets carried, and it changes everything. So after those lines, you're annealing and getting rid of stresses and things like that. So you can imagine that if that's the sort of temperature you need to get rid of stress and residual stress, it's also the sort of temperature that'll just turn it into a plastic mess and allow you to do anything to it. All right. Have you guys done anything on probability? Are you guys the guys that have missed that on the way through?
Correct.
Correct. All right. You will do it soon. You'll do it for thesis, I think. You'll have courses on it for that, which is helpful.
Weeks away.
Have you guys seen anything around a bell curve? Do you guys understand anything about bell curves and experimental data, the way it actually lays out? Cool. So that's pretty much all I need you to know, right? If I said the word standard, the phrase standard deviation, would everyone look at me stupidly, or would you guys have heard that phrase before at least? Standard deviation? Yes, good. All right. So, remember what we're dealing with here. This is our SN curve, and it looks something like, what was that, SUT, and it kind of did this thing, and then it did that thing, and then it did that thing, and that was a 10 to the 6, and that was a 10 to the 3. And we called this SM dash. Right. That's the curve that we're actually assuming is correct, right? Well, what actually happens, this has points on the curve, and you've got some data up here and some data down there, and this might be that's your experimental data. Okay? The line that we're dealing with is the average, the mean, the very middle. The data above the line, better or worse? Higher SN, higher endurance limit, better. Yeah, we don't care about that, that's good. If we use this line, we're taking care of all of that data. We're completely sweet. Data below the line, better or worse? Worse. Yeah. So we've got a problem if, and remember this is the average, so half of our data is below that line. So half the time we're going to fail before we're expecting. That's a problem, right? And we need to deal with that. So the way that this data lays out, if we took a single dot point, it actually lays out in a normal distribution. It's nice data. And that normal distribution looks like the graph there, where this is our mean in the center. So SN dash, which is this point, this point here. Half the data's to the right, half the data's to the left. Now obviously this is a frequency curve, so most of the data's close. That's why you have this peak in the center, because most of the data is close. Some of the data tails out. And the further away you go, the less data points, to the point where, effectively you have no data points if you go far enough away from that mean. That's what a standard deviation is. And we have numbers, really well characterized numbers, for how many data points fall within particular ranges. So a standard deviation, you can calculate a standard deviation, which is just kind of a change in SN in each direction. So these are evenly spaced. And you see there that we have 34.1% is in one standard deviation in each way. And then in the next standard deviation we have 13.6% of the data falls there, and 13.6% of the data falls in there, and so forth. Alright, so effectively we're saying that what is 34 and 34 is almost 70% of the data is going to fall in here, and then you add another 26, so what did I say, 70, 90, so another standard deviation, you got 90% of the data, you're almost everything, right? So, if we know what these standard deviations are, we can actually calculate a change in this that will allow us to shift this curve down to whatever confidence we want. So let's say we want 90% of the data to be covered by our calculation. We can work out a value that moves this down so that it covers 95% of, or what did I say, 90% of those dots. That's what we're doing with reliability factor, okay? Now, we don't care about anything to that direction. We're going to say that whole 50% is ours. We're good, because that's this way. So all that 50% we're already covered for. And all we need to add to that is how many standard deviations down this way we want to go. Right, so let's say we add one standard deviation down here, and we calculate a value that moves this down an equivalent to one standard deviation. We'll end up with this 50 plus 34.1 gives us 84.1% of the data will be covered by that. Alright? And the equation that we actually use for CD here is 1 minus 0.08 ZR, where ZR is the number of standard deviations from the mean. So let's say 1, so that's 1 minus 0.08 gives us 0.92 is our factor. Alright? And 0.92 buys us 84.1% of the data. So 84.1% of the time, you won't fail. And if you've got a factor of safety of 2 on top of that, maybe that's okay. If you want it a little bit more reliable, you can go an extra standard deviation, and so that's 1 minus 0.08 times 2, which the factor is 0.84. So if you decrease this by a fraction of 0.84 down to about there, then now you're covering 97.7% of the data. Are we feeling more confident in our experimental data yet? Yeah. So the further down you go, the more confident you are, and the more of those little dots you take, and the less likely it is that something you have will break because you've only taken into consideration half the data points. Alright, so this is statistics that we need to implement into every single experimental results that we use. This is just carrying it out in a very kind of simplistic way. Now, because 84.1% and 97.7% are kind of crap numbers, top left of your table, you've got some, it's kind of, if you did that for half standard deviations and quarter standard deviations and whatever, we've changed it into in terms of numbers that are recognisable. For example, on the left there, for 50% reliability, factor of safety, the modification factor of 1, which makes sense to us because at the exact value that we have, so not changing the value we have, half the data is good, half the data is crap. Right, so 1. Then you've got 90% is 0.897, then you've got 95% is 0.868, 99%, 99.9, 99.99, etc. To the point where if you want basically every single value, you're talking about a factor of about 0.52. Alright? Now, we don't go all the way down to that. Ordinarily, we deal with about 90 to 95% reliability factor is a pretty reasonable number for most analyses because we have other, factors of safety and things in it elsewhere. Alright, but you'll be told in a question what reliability factor you need to know, and from here on in, all you need to do is read that table and write a number down. Okay? But, as with, I'm trying to make everything in this class give you at least the background of where stuff comes from, such that at least you understand why you're doing it. It's pretty important when you talk about ANSYS, because ANSYS does some of this process for you, and the data that you put into ANSYS, the material models for steel actually encompass a factor around the probability of the experimental results. So when you use our idealized thing for steel and you compare that to what you get out of ANSYS for steel, they'll be different by a factor of 0.8 or 0.7 or something. It's because ANSYS is already doing this, which means when you do the ANSYS analysis, you don't need to do this again. Okay? So you need to understand this stuff, and when something looks wrong, you need to try and dig a bit deeper, and that's one circumstance that caught me out because for 6 months I stared at it and tried to look up different documentation to tell me why ANSYS was giving me a different number to what I knew steel needed to be, until I actually worked out the numbers lined up with this, and that's what they were doing. Okay? Some standards, the British standard for welds incorporates a lot of this stuff as well in fatigue of welds and things. So when you see these numbers, try and interpret what they are rather than just a value that you put into an equation. Easy enough? Alright. Last one, CE, basically you don't need to worry about it. I'm putting it there, and I always put it there because it's effectively you demonstrating in every single analysis that you provide to me that you understand that this may not be the full picture. Right? Miscellaneous effects can be anything around residual stress, directional material characteristics. So talk about carbon fibre, it's very directional. But obviously steel can be directional, particularly if you've cold drawn it, hot drawn it, tempered it or anything like that. Corrosion, obviously we have a surface factor for that, but corrosion can be more important than that and have extra negative effects. Any sort of plating or painting, if surface finish is a factor, then doing something to that surface might be a factor as well. Alright? Hardening a surface might have an effect. So we're not analysing those things particularly, but I require that you write miscellaneous effects CE equals 1, just to tell me that every time you do an analysis you think, is there anything more that I need to think about? No, we're good. Alright? And then, if you actually do something in practice and there is something more you need to think about, then you have to work out an approximate factor that's going to have, some sort of effect that's going to have. And that might be through research, it might be through experimentation, it might be through blind guessing. You need to actually take something into consideration if there is something else going on. Okay? Alright, and that's all our factors. Now, I have put the main parts of that on the handout that I've put on each of your tables, because obviously there's lots of slides and I can't have a slide up while I'm asking you to do a problem at the same time. So that's why I printed them out for you. But we're going to do a couple of simple problems. You guys have a go at it and then I'll help you through it. And then we'll call it a day.
That was just
Yeah. Oh yeah,
they changed everything. This is a
Oh, that looks swap. Project thing.
Alright, so we're getting in the realms of questions that have lots and lots of information in them, and you need to highlight that or at least not miss it. So we have a force, really simple problem. You guys can smash out some of the forces stuff really quickly. Please put some assumptions after this, lay it out properly. Your assumptions at the very least are your elastic and homogeneous one, your weight negligible one, your transverse shear one. Bare minimum of 3 assumptions at each problem. Now, we have forged steel. That's important. That tells you surface finish. SUT 800 megapascals obviously gets used in lots of different places. Fully reversed tells us that what we're doing is appropriate, because once you know how to analyse a few different things, that's important information. So that's telling us that F goes down, F goes up, F goes down, F goes up in even numbers. Applied with 95% reliability, we just finished talking about that. Infinite life means you use that Sn at 10 to the 6 value, so Sn dash to 10 to the 6, sorry. In some circumstances I might ask you for 10 to the 3, but almost never. And a factor of safety of 1.5. Alright, lots of information there. What you need to do is write your assumptions out and then start laying things out. So the first thing, follow that flow chart. The first thing you're going to do is all of that free body diagram business. Guys, when I actually work through this, I'll show you the way that I want it laid out. But effectively, for each of these, so you do the wrong one. You do all of your normal stress calculations first, so your free body diagrams and your stress elements and stuff like that, so the first parts of the flowchart. And then I'd put a heading for endurance limit. I'll pop it over here just so I don't drop that out. Sn. And at that point you put your equation, Sn equals Sn dash Ca, Cb, Cc, Cd, and Ce. And for steel, Sn dash is approximately equal to 0.5 SUT, and then calculate that. And then put a heading for endurance limit modifying factors. And at that point, you can say Ca, what was that, size factor, and then any information you need, any assumptions you've made, and the actual calculation for that number, and then Cb, any calculations, assumptions, anything, Cc, anything, and so forth. And at the end, you say Sn equals whatever you end up with. What's our ultimate tensile strength here? 800, so Sn equals 400 times your 5 values, and you'll end up with an Sn result. Okay, so that's the way I like these to be laid out. That way you've got the assumptions and all of your information, your explanation of what you're actually doing in line there. So does that largely answer your question?
Yeah.
It's assumed that you know how to do that. If you don't, then yeah, you will. It's a requirement of that subject. If you haven't, then it's an omission. It will be in that textbook extensively. Yeah. All you do is
we've done like
yeah. So it's in the magnet, you calculate the relationship it is at a sensor based on the point load, and then it's used to you do it, double checking that textbook. But yeah, absolutely, you need to be able to do distributed loads for exactly this. Alright, so in terms of layout, and to save time, because obviously you've already done this, I'm going to assume that you've got an assumptions section, whereby you assume a couple of different things, weight being negligible and so forth. And then I assume you have a free body diagram, shear force diagram, bending moment diagram, and something in a stress element identification that might look something like this. And what do we got? We got tension at the bottom, so I'm just going to analyse the bottom element like so. What's my actions? Alright. Sigma X. And I've got sigma x equals mc on I, which I have as 0.05 F. Where's that? That's oh, yep. I did it. Times 0.01 divided by 1 on 12, 0.025, 0.02 to 3. I get as 30,000 F. So whatever I got? 30,000 F? Yep. Do we have any stress concentrations to apply to that? No. So we can just ignore that part. Or KT equals 1, 1 minus 1 equals 0, KF equals 1, and you can put it to the front, but there's absolutely no point wasting your time. Alright, and then we do our layout thing. Looks exactly like that. I'll get rid of this and start it over here. Alright, so endurance limit. Sn equals Sn dash, and then all the factors. For steel, Sn dash equals, is approximately equal to 0.5 SUT, is equal to 0.5 times what we have, 800? And that equals 400 meg. Good. Alright, and then along the lines of the layout that I've been talking about, something like CA, size factor, and then we've got, what have we got? Rectangular and bending. Bending. Fine, equivalent. D, and so D equals 0.808 square root of HV, and that's all in millimeters, which gives me 18 millimeter equivalent diameter. Everyone get that? Yep, cool. Might go up there. Some of you might not be able to see up here. It's a terrible little board for a lecture in this room, sorry about that. Okay, so therefore CB equals 1.189 times what is 18 to the power of minus 0.098 equals 0.896. Did everyone get that? Yep, everyone double check that your number was less than 1 but greater than 0 and working with the millimeters in there and whatnot? Cool, sorry that's 8. Alright, CV is, what do we say CV was? Surface factor, is that what we're doing?
Yeah.
And it's always useful just to rewrite what you've been given. So in this case we've got forged, well the information that you need for the calculation, so forged and SUT equals 800 meg. From figure 8.13, CB, what did everyone read that as? 0.38. Any difference? Yeah, 0.375 or something like that I said, I think. 0.38. Sounds good. Alright. CC, CC is temperature, yep, good. What do we do here, guys? What temperature is it? No information. If it was hot, obviously someone would tell you, or you'd hope someone would tell you. So at this point you just say assume T less than or equal to whatever that criteria was. What was it, 450? C. Therefore CC equals 1. What's that? CD reliability, and you're told 95% reliability, which you can read a number straight off the table. What number do we get? 868, excellent. And last one, CE, miscellaneous, and I just say none. CE equals 1. Alright, but as I said, obviously these ones we're not having any miscellaneous effects, but when you're actually doing this, just put it in your workflow so that you kind of think about that every time. Alright, so therefore, S, that's a terrible S. Sn equals 400. What was our first factor? 896. 0.896. Oh, there it is. Yep. And 0.38 and 1 and 0.868 and then 1. What do we get for that? Say again. Closer than about 117.18 megapascals. Close enough. Good. Alright, so let's look at that for a second. Started with 800 megapascals. And look where we've got. Yeah? Big difference. Really big difference. 800 megapascals is probably 400 megapascal yield stress, or maybe 500 megapascal yield stress for a material like that. We're a lot under that. Alright, and we've only included a couple of pretty simple little bit of reliability. This isn't even including a factor of safety yet. Bit of reliability, bit of a change for surface, so as forged, it's bloody terrible. And we might want to deal with that. But if we got to this point, or we get to the end and it doesn't carry the load that we want, what we can do is go back to all of these factors and say what really screwed us up. And that's a good one. So as forged, alright, maybe we need to machine finish something. Or particularly in the critical zone, maybe we need to clean that up a bit, grind it or something. So this is a real indicator of the importance of fatigue and the effect that fatigue can have on your strength. Right, well the last thing to do is rearrange that stress equation as necessary. And I just gave it a heading. So that's checking failure, something like that. N equals, what do we have? Sn on sigma dash. So our von Mises is equal to the square root of sigma x squared plus a bunch of stuff, which is all 0. Therefore, that equals sigma x. Yeah, everyone good with that? Remember, don't forget to do the von Mises step. Therefore, n, what was n? 1.5. 1.5 equals 117.18E6. Don't forget to put that on, because we're dealing with newtons and we want to end up in the right place. And that's what, divided by 30,000 F. Therefore, F equals, what do we get? Numbers for F, anyone?
2,600.
2,600, anyone else? 2,600? Yeah, plus or minus. So all of these factors, some of them will have a little nudge factor. Some people will read one thing, some people will read the other. So, plus or minus maybe 100 meg, maybe less than that. 100 newtons or less. So let's say 2600 newtons or thereabouts. And the last thing that we do is just recall that that's 2,600 down, 2,600 up, 2,600 down, and over and over and over again forever, ideally. Cool. Makes sense? Easy enough? That's probably time. I don't think we need to do another one. I'll put another one online that you can follow through. If anyone has any workshop questions that you haven't asked already, feel free to come and ask me. Otherwise, I will see you guys tomorrow.